Swayam Prabha. Digital India. Educated India.
Good morning. Let me continue where I have stopped last class. In my last lecture, actually I have discussed normally consolidated soil, over consolidated soil, and how to determine for a normally consolidated or over consolidated soil total consolidation settlement. And I will take some problem later on to illustrate those whatever we have derived, and right now I will just try to continue with the consolidation, time consolidation. That means we know that if the saturated fine grained soil is subjected to a pressure, then it will undergo consolidation. And now the question is how long it will take to complete the consolidation. So, that is the one most important, and what is the some soil because of its characteristics may quickly consolidate, some soil may not, it may take longer time. So, it depends on soil property, and before going to development of that time consolidation, let me see what is the mechanism of consolidation, how it happens. Before that, I just since I am talking about consolidation settlement, and I have also mentioned that there is a elastic settlement. So, in comparison to this, actually different soil will have different types of soil settlement, and we can classify three different types of soil, that is sand, steep clay and soft clay. And we know that sand actually a majority contribution is from elastic settlement, and so you can see that this is due to elastic settlement. This is 70 to 90% is from the consolidation elastic settlement, whereas steep clay, the out of total settlement 40 to 60% for from consolidation, as soft clay it is 10 to 25% come from elastic settlement and rest will be constant. That means, when you talk about sand, the elastic settlement important, when you talk about soft clay, then it is consolidation settlement important. So, now we will see the mechanism of consolidation. That means, you can see this is a mechanism I have shown here. This is little sketch, little problem is there. So, but anyway, I assume that this is sealed, actually they are sealed and no friction. Okay. There is no friction here, and initially there is no opening at this point, and then if you apply load through this piston, suppose assume this is a piston and it is filled up with water and there is a spring. Now, if I apply this load, since the water is incompressible, so until unless this piston goes down, load will not transfer to the spring, and the spring that the piston to go down, what you need to do, that means water to be has to be compressed, but you know that water is incompressible, and because of that what will happen, that the water will be pressurized. That means, there will be pressure will develop within the within the soil water, and it will be under pressure actually. So, if I apply some amount of load P, that same magnitude actually equal pressure will be developed within the water, but still there is no transfer of load to the spring. Now, in the second stage, if I imagine a small opening here, and then what will happen, it is very it is not so big, suppose very fine opening is made, then since the water is pressurized, it will try to get released. So, what will happen, then water will try to seep through this small opening, and whatever excess pressure is developed, that pressure until unless the pressure is becoming 0, it will continue to come out, and when it will come out, the volume will be reducing, and because of this volume reduction, this one will be going down, and when it goes down, the water no pressure, that means what is the additional pressure, where it is going to the spring. That way actually, that is the way the load finally transferred to the spring. In the soil also it will be similar thing will happen, where through the grains, contact to contact grain, the soil mass is formed, and when we apply the load through the surface, then until unless this void space is reduced, then that void space is reduced, there will no compression will take place, because both soil grain and water is incompressible. So, until unless water is coming out or void is reduced, that actually soil will not compress, and until unless compressed, then whatever additional load you apply to the soil, that soil will be transferred to the water. That means, water will be pressurized, and that pressure is called excess pore pressure. So, within the soil mass, when you apply the load, immediately after that excess pore pressure will develop, and over the time, when through interconnected void spaces, the water will try to seep through and release the pressure. So, when this mechanism will be completed, that means by seepage of water, when completely excess pore pressure is dissipated, that time actually called complete of consolidation. That means, whatever load you have applied, that load finally transferred to the soil grain, and then after that, because of that, the soil grain will come closer and the consolidation will be completed. So, this is the mechanism, that similar way, when it is a sealed container, when you below there is a spring, but if I push the piston, until unless water is coming out, the load will not be transferred to the spring. The similar mechanism where there in the saturated fine grained soil, if I apply load onto that, until unless the some amount of water is coming out to have the volume change, that actually this extra load whatever you have applied will not transfer to the soil grain. So, that is the mechanism of consolidation. That means, immediately after applying the load within the soil, whatever water is there, they will be pressurized in the form of excess development of excess pore pressure, and with time this excess pore pressure will be dissipated, and the external load will be transferred to the soil grain, causing the compression, and that compression is called consolidation. When the excess pore pressure will become to the 0, that is called completion of the consolidation settlement under that particular load. So, this is the mechanism. Now, when you apply the load on the surface, generally the pore pressure development will not be uniform generally, and it will be different places, it will be different. When there is at a great depth, there is a thin layer is there and load is applied here. Boson's theory and other that it will be with depth, the pressure intensity reduced. Okay. So, that means, at this point whatever pressure at this point different pressure will be there, and if there is different pressure initially, the pressure will be countered by the development of excess pore pressure. So, pressure will be here and here, then it will be more here, it will less here, but if the layer is thin, we generally consider the uniform and at the middle of the clay layer, and with that for all practical purpose we can work. So, whereas if there is a load is applied like this, and then it is a over the depth pore pressure from here to here, if I want to imagine, then pore pressure will be maximum here and pore pressure will be minimum here, and at some depth it will become 0. Why it is so? Because of this loading, pressure is decreasing over depth. So, pore pressure also will be less. Similarly, if it is a newly deposited soil, and in that, because of this soil weight only, it will have more compact here and lesser loose here. So, these places immediately pore pressure will be dissipated. So, because of that, when you go deeper and deeper, pore pressure intensity will be more. And suppose that there is a thick layer and load is applied here, obviously there will be different trapezoidal distribution will be there, more here and less here. And in the other case, suppose a embankment, newly constructed embankment with some loading, in that case because of this newly deposited soil, the pressure will be like this. Sorry. Because of this load, pore pressure is like this, and because of this loading, pore pressure will be like that, similar to this only. So, these two together will have a reverse trapezoidal. For this normal condition, trapezoidal will be here, less will be here, and newly deposited embankment, there actually it will be also trapezoidal, but lesser intensity will be at the surface, more intensity will be more pore pressure will be at depth. So, these are actually before going to develop the rate of consolidation, we need to know how pore pressure developed at different depth. So, this is the visualization, we can visualize for different condition how pore pressure distribution will be there over the depth. And then another thing is we know that another important term is that degree of consolidation. So, degree of consolidation U, that is consolidation attained, suppose in a particular load, suppose if I apply P load and under that the total settlement at the end of consolidation, suppose delta, and at time t. So, with respect to now, and this one will take suppose a capital T time. Now, if I want to find out what is the amount of consolidation will take place at a time t, some different time between less than t. So, that is what is defined, degree of consolidation is defined as consolidation attained at time t, at any time t. So, that is suppose delta t and divided by total consolidation suppose delta. So, total consolidation is delta and delta t at time t. So, that ratio is degree of consolidation. This is the another term will be used for our time consolidation. So, whatever I have explained in the last slide in the schematically, once again it is listed once again. Unit distribution can occur in thin layers, that is what I have mentioned, thin layers, though it is different, but in practical purpose one can use the ui can be as delta sigma, that at that depth whatever delta sigma, because of this loading at the surface, that can be taken as a ui, that initial excess pore pressure. And for triangular distribution is found to deep layer under foundation, where ui varies from maximum value at the top and at a negligible value at some depth. Because why? Because actually the immediately after loading the pressure will be more on the soil, and when go deeper and deeper pressure will be less, and this pressure will be countered by the pore pressure only. So, because of that at the near surface pore pressure will be more, and at the greater depth pore pressure will be negligible, and sometimes it will become 0. And similarly, a triangular distribution with ui equal to 0, that is newly deposited, because there actually since is a loose, and immediately after deposition there if there is a pore pressure development, immediately it will be dissipated. So, at the top of the layer and ui equal to a maximum value at the bottom can occur for a newly placed layer of soil. So, because of this reason already I have explained, and a trapezoidal distribution results from the quite common situation of clay layer at some depth below the foundation. That means, if the thickness is quite large, and because of that distribution of stress will be more at the shallower depth and less will be at the greater depth. So, as usual, because of that there will be trapezoidal distribution with more at the shallow depth and less at the greater depth. And just reverse, for a new embankment carrying superimposed load, a reverse form of trapezoidal can be seen, that means it will be like that. Okay. So, this distribution pore pressure distribution will be, whatever we could visualize, will be useful to analyze later on. Now, the consolidation settlement, that will be a theory developed by Tarjagi first, that is actually one dimensional consolidation theory. Later on 3 dimensional consolidation theory also is developed, but we will concentrate right now on one dimensional consolidation theory proposed by Tarjagi. And for any theory, we know that we need to have certain assumption, and if you deviate from the assumption, then this will not be applicable. So, those assumption as given by Tarjagi is the soil is saturated. We know that is very important, because the consolidation is the phenomena for the saturated fine grained soil. So, saturation is the must. If it is not saturated, then consolidation will not be there. The coefficient of permeability is constant. We know the coefficient of permeability can vary different direction, but and different depth, but for the development of this theory, we assume the permeability of coefficient of permeability is constant, particularly within a particular layer. Darcy's law of saturated flow applies, K proportional to I, that is also to be valid. The resulting compression is one dimensional, that is another important assumption. That means, if there is a clay layer, and if I apply load through the soil, then your compression will be one dimensional, that means it will go, assume that to go like this, but normally if I apply load like this, the compression will be something like this. So, it will be, when it will be compressed, this will be displaced this side. So, because of that it will different, but for the initial development was assumed in the initial development, it was assumed that resulting compression is one dimensional, that means only compressing vertically and no other lateral expansion or contraction. Water flows in one direction. Actually, see, water, when there will be water is in it and it has to be dissipated. So, water will be flowing in one direction, vertical, or not together vertical or horizontal. Volume change are due solely to change in void ratio, that is another important. You are that means we are not soil grain, because of the loading, if soil grain compressed, that is not applicable. Here only, as I also mentioned in the mechanism of consolidation, that the volume change or compression takes place because of the volume reduction or void ratio void reduction. And void reduction, how it happens? Initially voids are filled with water, when water goes out, then void become empty, and there is this soil grain is loaded. So, that because of that soil grain will come closer, completing the void spaces. So, that is volume change also because of only change of void ratio, no other compression of water or compression of solid particles. Now, to do this, whatever we have done in the while discussing the permeability topic, that flow in and flow out, and that time we have derived the expression. You can see the expression for flow in saturated soil already established. the rate of volume change in a cube of volume dx, the volume of cube support dx dy dz, and then volume change, rate of volume change, we have derived this expression before. So, kx d2 del 2h del x square plus ky del 2h del x dy square plus kz del 2h del z square dx dy dz. This we have derived before, and for one dimensional flow there is no component of hydraulic gradient in the x and y direction, and putting kz equal to k, the expression become, if I consider one dimensional, the expression reduces to k into del 2h del z square del 2z into dx dy dz. Now, volume change during consolidation is assumed to be caused by change in void ratio. So, the porosity I can consider N equal to V b by V, and it is again can be expressed E by 1 plus E. So, from here I will just see again volume change, since it is based on change of void ratio, I will try to correlate, and you can see. So, you can see from the previous expression V v by V equal to E by 1 plus E. So, V v will be now, or V is equal to, this is nothing but V into E by 1 plus E. So, another expression for rate of change of volume is therefore, so this is the one del t with time dx dy, and this is another expression for volume change. So, equating these two expression, we can get k del 2h del z square 1 by 1 plus E del E by del t. Okay. The head edge causing flow is the excess hydrostatic head caused by the excess pore water pressure U. So, that means there is a H and U, there is a relationship. So, H will be equal to U by gamma W, and if you substitute, then this become, and if I instead of H, if I now express in terms of U, then this one will be reduced to this form. Okay. So, after that you can see again with one dimensional consolidation there are no lateral strain effects, and the increment of applied pressure is therefore numerically equal to the increment of induced pore pressure. Hence, an increment of applied pressure dP will cause an excess pore water pressure du. So, always it will be reversed. So, du will be minus dP. So, if I do that, then we know dE by dP equal to A, and that will be equal to dE by du. So, we have got actually initial E versus pressure relationship, we have got dE BP, dE by dP is A, and here actually we can write actually dE by du, this one in this form. That means, I want to, since the consolidation is a result of change of void ratio, I want to express in terms of void ratio, that is what we are planning. Now, if you substitute those, then it become in this form, the equation will come to this form, k gamma w 1 plus E del 2 del z square A del u del t, or C v into del u del 2 u del z square equal to del u del t. And now, we are taking this one, C v is defined a coefficient of consolidation, which will be k gamma w A into 1 plus E equal to k by gamma w. So, C v, that is C v equal to k by gamma w m v, or C v equal to k by gamma w A, k into 1 plus E by gamma w into A. So, either way, so that means whatever term we have got this, if you take this side, then whatever things we are getting, those all together we are defining it, or we are introducing by a term that is called C v, which is denoted as coefficient of consolidation C v. And so, this is also time to time required, sometime by using consolidation settlements we can sometime find out the permeability, if you remember this formula. So, C v equal to k by gamma w m v it can be utilized in some cases, or by using this equation also you can find out k. So, these are also sometime consolidation test sometime used for determining indirectly determining permeability also. So, ultimate equation become C V into del T U del Z square equal to del U by del T. This is a particular form of equation and mathematical equation, partial differential equation, and this will have a standard solution. So, you can try to solve it for U. So, in the theory Z is measured from the top of the consolidating layer and drainage is assumed at both the upper and lower surface. Thickness of the layer is 2h, that means, so upper and downward direction, this thickness is 2h, and the initial excess pressure u I equal to minus dP, and the boundary conditions are at z equal to 0, u equal to 0 at the surface. When if there is a load is applied, so at this point immediately the pore pressure will be dissipated because it is a surface. So, it will become 0, and at z equal to 2h, that means, at this point if there is a drainage provision, there also become 0. At t equal to 0, u equal to u I, so and t equal to 0, u equal to u I. So, a solution for this equation, this particular equation, generally mathematics, you people are handle mathematics, and you know if this is the type of equation, what will be the form of solution. This is the solution can be assumed, and then this boundary condition can be applied, and if you apply this boundary condition, then you will get you can see where u I is the initial excess pore pressure uniform over the whole depth, and sorry. So, that whatever expression we have assumed as solution, there u I is the initial excess pore pressure uniform over the whole depth, though I have shown at the beginning that pore pressure distribution can be different, more there at top, but less at top bottom, less at top, more at bottom, but for the initial development we are assuming u I is uniform throughout the depth, and capital M is this one, where our small m is the positive incidence varying from 0 to infinity, and t is the time factor. This is a time factor, and this is the expression, very useful expression, you have to remember always for finding out the time to complete a particular degree of consolidation. So, CVT square by Z. Because of the drainage provision at the top and bottom of the layer, u I will immediately fall to 0 at those points. With the mathematical solution, it is possible to determine u at time t for any point within the layer. If these values of pore pressure are plotted, a curve can be drawn through the points. The maximum excess pressure is seen to be at the center of the layer, and for point at the, so that means you have this is the initial excess pore pressure, and immediately it will become 0, it will be 0, but pore pressure will be at any time at any depth, so it will be not 0. So, it will be something else. So, different point actually if you find and join them, if you got a curve like this, that is called isochron. So, for different time interval, different time isochron can be obtained. So, that I will show you in the next slide. The maximum excess pressure is seen to be at the center, that is, you should see at time t 1 this is maximum, or t 2 this is also maximum, t 3 also maximum here. So, like that whatever may be the time, that isochron giving you middle value at the midpoint or midpoint of the layer. The isochron are shown here in the next page. So, I will show of course, in the next one. After a considerable time, u become equal to 0 and delta sigma will equal to delta sigma dash. Plot of the isochron for the different time intervals. So, I will show the next one. for a particular point the average degree for the degree of consolidation from the definition is u I minus u z by u I at a particular point u I minus u z by u I. So, u z is the total and u I minus u z that will be whatever happened actually at particular time divided by the initial and what happened at a particular time u I minus u z, that means what is the present consolidation and u I is this. So, these two ratio this is the ratio that is called degree of consolidation we have defined before. The mathematical expression for this, if I do this, then from there u z become this and average degree of consolidation expression I will show the isoscron. From there I will show you that what is average degree of consolidation u 2 h u I, that means area whole area initial minus area of isoscron, that means whatever consolidation took place divided by this, that is u. So, let me go to that one. You can see these are the isoscrons. So, initial pore pressure is like this. Initial pore pressure is this one and at any time suppose this much dissipated. So, this is actually transfer of and this is yet to be dissipated. So, like that at different in time interval. So, at t infinity when full pressure is dissipated. So, your u become 0, u become 0 and at an initial time t equal to 0 delta sigma 1 equal to u I, that means whatever stress you have applied that itself will be equal to u I and slowly u I will be reduced at a infinite time, which is a sufficiently long time. After that t at infinity your u become 0. Now, when u become 0 that means it is full consolidation. So, now based on this a final expression for mathematical expression for u, based on that this is the final expression and I will see in my next lecture how to utilize this relationship between u and t to find out the time consolidation. Thank you.